Hello everyone, welcome to another edition of Learning Glass, pandemic style. So today we'll talk about materials, fundamental mechanical behavior of materials, and a couple of applications to manufacturing. So today we're talking about stress, strain, curves, which is some textbook stuff, stress strain curves, and not only textbook, but very useful in a lot of applications and basic material properties, and manufacturing. So the stress strain curves, one way to think about it is that this is a cause and effect. The induced stress, some force on the body produces a strain. Cause and effect of mechanical force. So the cause is the mechanical force, and the effect is the strain that the material undergoes upon having the stress. The stress is the elongation, is the deformation. The strain is the force. And it's useful for material properties and material limits. So material mechanical limits. So for this, what we're looking at is forces and elongations and deformations. So the normal stress that can, in a standard test, can be done by tension or by compression. It's the force over the area of this material, that the cross section that this force gets put on. So by definition, this is the normal stress. So I should put this here. Normal stress by definition equals that. And you can use the typical symbol to use is this sigma here. And I'm going to put a T here, true. Or I'll just put that, I'll specify later because we may remember that it depends on which situation you're talking about. And then you'd have the strain, by definition, is the change in shape with under this certain force. So most of the time that we're talking about uniaxial, one-dimensional strain, or in terms of the textbook. So one way to define it would be, upon experiencing this strain, there's some change in the length. So per each, like from some integral of some initial length, let's say LO to L, when you undergo this stress, it's going to deform. So what does this pathway look like? What is the response of the stress to the strain is a response to the stress. So if you're starting at a certain length, how does that look as this various levels of stress are applied? So the most general way would be to describe it this way. And if you were to say, okay, let's apply these definitions of the area, that every time you have a force, it's going to be acting on a certain area. So let's account for every time we change the force, let's also look at the area. So the true stress accounts for changing area, cross-sectional area. Because the volume is conserved sometimes, the volume is not conserved sometimes, but the area does change most of the time. So we'll call it sigma true equals this force that's applied at one given test over the force, the area that might change with force. So this is area, and it depends on the force you're applying. Similarly, true values, so true stress and strain, account for this change in area. So depending, I didn't put the symbol here. So depending on the force, the area might change. And then when you're counting this in your integral, if you were to do this integration with the changing area, you would get that the true strain is the natural logarithm of the h, or the length that you show at one time. So let's say length with respect as force changes over the initial length. So these are saying that the area changes with the force, as we may imagine, and the true values give you this local behavior. But as we also know, engineering stress and strain are useful for standards and convenience, for standard tables and such. It's easier to just measure the initial size. And those are, I'll just put these as a normal sigma that you might see more commonly, would be that this is the force over the area that you begin with. So this force changes, and this is the area that you begin with. And the strain would be a change in length after this force is applied over the initial length. So true is actually keeping track of the more detailed physics, more general physics. This is just a more convenient that we normalize it by the initial area and the initial length that we have of this material before it undergoes these stresses and strains. So let's draw a typical table. I'll go ahead and erase these here. Yeah, so in general, stress is a force over area, and as we may remember, the units of these stresses is pascals in SI units. That is because Pascal is force per area, and we're talking about fluid analysis of fluids, pressures exerted by fluids. This is called pressure. That's the property, thermodynamic property of pressure, or mechanic property of pressure. It's force per area. It's the same idea that a fluid, molecules or gas molecules, they exert a force on the chamber walls, and that's a similar concept as normal stress, but in the context of materials, we call it normal stress. There's other types of stresses as well. Okay, so a typical stress-strain curve would have some certain common features depending on the material. So this would be the strain, which, for example, can be the millimeters of change per millimeter that you began with, or the instantaneous true values. The stress would be in units of megapascals. So this is same units of pressure because it's force over area, but this is the mechanical sense. Most of the time when we're talking about normal stress. So I'm putting this value of 300, and let's say over here, 0.18. So this would be like for an aluminum alloy. Aluminum alloy, which is a ductile metal. This is the typical magnitude. From 300 megapascals of normal stress, you would have this amount of strain induced. And if we were to have this first notch here of 0.02 in the strain, millimeters per millimeter, how this particular alloy behaves would be if you start to either pull this in tension or compression. If it's compression, this will be negative. If it's tension, it'll be pulling. So this ratio would be positive. You would have a region where it has a very linear relationship between stress and strain. So let's say going up to, from here all the way up to, let's say here-ish, you'll have a linear relationship. And as a matter of fact, if you were to pull this under tension and apply this amount of stress, you'll have this response in this elongation. And if you don't go too far up, it will go back and relax back to its original shape, its original length, because that's the elastic behavior. Where as long as you don't apply too much normal stress on it, the strain will be able to go back to zero strain elastically. That's the elastic limit. But for this particular material, as we may remember, what happens if you go too far, this slope changes. So the benchmark of where this slope changes from sharp linear to something more with a bigger strain, this benchmark here is the so-called yield strength. There's a lot of ways to define it. The most, in all cases, you could always say that this is where the strain increases rapidly than it did before. Strain increases more rapidly than it did before. There's other criteria you can apply. And then there's also other ways you can break this down, because there's also a limit where before the yield strength, it'll still go back elastically, but it's no longer linear. There's still a little bit of room there where it'll still recover elastically. So this is the elastic deformation region. When you apply this stress, it deforms, and the deformation is quantified by the strain, but that deformation is elastic, meaning that it'll go back to its original elongation, to zero strain. Then, once you have this, beyond this yield strength, the strain changes more rapidly, but on top of that, you also have a different regime of behavior. This is it's plastic deformation. Plastic deformation, well, all of this is plastic deformation, but also it's also where the material gets harder. And then this is what you see here is that the material is going to stay in that position to some extent. I'll explain what else happens, but the material does get harder. So if you did bring this material here and you did relax it back, it is going to relax to some extent, but not that much. So if this is the slope of the elastic region, if you go this far and you stop, it will relax a little bit. but it's going to have some offset. So it is going to have, it still has some elastic behavior, but it's not, this slope is not going to change. If you do stop here, it is going to relax a little bit under tension. It'll go back a little bit, but it's still going to be deformed. And so this would be like an offset. If you were to do here, this would be a slight offset. So this would be the new zero strain, or it's going to be strained. But if you could start here another, if you didn't know the history, this would be the new zero strain. If you did not know the history that it already was plastically deformed. Okay, so that's one thing. And then if we go farther here, the ultimate strength is where this peak happens. And it'll still, it won't take that much force to give it some elongation, and it's going to start, acting weird until it finally has failure. And this is also where necking would begin to happen, meaning the diameter is going to shrink for a standard tensile test. And another thing, so I'll put this here. That's the ultimate strength. But if you were to, this is engineering stress here. So this one is the engineering version. The true version looks similar, except that it's higher, because the area decreases. Because the area decreases, you divide by a smaller number, and this integral is slightly different. You'll get higher values in general. Okay, so this is where it fails, where it breaks apart. So for the elastic region, you have reversible deformation. It'll relax back to zero strain after you release this normal stress. And as we remember, this Young's modulus, I don't know how to spell. This Young's modulus is the slope of this elastic region. So it would be if you're assuming you're elastic, it'll be the relationship between the rise over run. But it doesn't apply once you're outside of that region. So when we're looking at this material behavior, this mechanical cause and effect, that you might want to stay away from some regions depending on your applications. For example, if we want to make sure our material does not deform and it can recover back to its original size that we intended it to be designed for, we need to stay in the elastic region. So this is an example. So if you were designing some structure with the desired shape and size, and that would be able to have some wiggle room, but in some cases of structural design, you would want to stay in the elastic region, where it would recover, or it'll have some given amount of strain under some stress. And that's more of this linear behavior. But if you're trying to form your material, you literally do not want it to recover. You want it to keep this original shape. It's going to relax back. It's going to have some spring back or some offset at the end of the process. But if you want to deform this, you would want to go to some irreversible deformation in the plastic region. So you want to go beyond the yield strength, when you're trying to deform. You start with a material, you apply these stresses to go beyond the yield strength, and it'll become plastically deformed. So this is where sheet metal forming operates. You have a piece of sheet metal, you want to bend it, you need to apply enough, you need to know the mechanical behaviors that'll give you enough past the yield stress such that when you bend it, it's going to stay there. It's going to have some offset, of course, but it's going to keep the shape you deformed it in for the most part. So if you want to form your sheet metal, or if you want to forge, if you want to stamp with a lot of pressure some slab or some piece just by applying this normal stress onto it, you want to make sure it's enough normal stress that'll keep you in the plastic deformation. And there's other manufacturing forming processes we can think of, like thermoforming. Okay. So let's continue. Speaking of sheet metal forming, it's forming of a sheet of metal. So what you do is you apply some stresses on this metal, and according to this the stress strain curve behavior of that material, you'll be able to design a shape based on the forces that it needs. And of course there's some limit to that where you don't want to have failure. Just by inducing too much stress, the material will fail. Okay, so for sheet metal forming, so this is our, let's say this is the sheet metal that we're forming. Some three-dimensional sheet. Okay, so let's say we're going to pull it from this direction here, this one dimension. So let's say we apply a tension, some normal stress in this direction. Tension, uniaxial tension. So this is going to be uniaxial tension, meaning it's just pulling from this one. This is the only place I'm applying the force on an isentropic material, meaning there's no favored direction. The stress strain curve in principle is the same in each direction. Uniaxial tension on an isentropic material. Even though it's isotropic, what's interesting is that when you apply this stress in one direction, all three dimensions react. So even for isotropic material, what will happen is for this given stress, of course, we're going to get this strain in this direction. The strain is going to appear, going to be generated. But according to this this theory of this deformations and these stress strain curves for three-dimensional piece, you're also going to have these negative stresses show up as well. In the other three, if we're talking about three dimensions, these other dimensions, this is dimension 3, so even though this is an isotropic material, it doesn't favor one direction, and we're only applying the tension in one axis, this is going to be the response. It's going to feel strains in either direction. So the way that this works is that this strain that you applied here is equal to the negative strain in the other direction, because it's compression this time in that direction, and then this so-called Poisson's ratio. the ratio of how the effect of one stress affects the other direction. And this is for elastic. Similar to Young's modulus, the Poisson's ratio only is defined for the elastic region. So you would have this Poisson's ratio. And then for the plastic, you would have volume conservation meaning volume is constant, and you can write that keeping the Poisson's ratio some constant value around 0.5, that E1 true, keep in mind that this you have to keep it 100, keep it true. The true strain in one direction plus this true strain in the other direction plus the true strain in the third direction equals 0. This will be the plastic regime. And you can use these so-called form limiting diagrams. So for sheet metal forming, there's this form limiting diagram, which is good for both one and two dimensional, one curve or two curved deformed sheets. It's based on the similar principle that there's some failure limit, there's some yield strength, and it helps you to determine how much strain these materials can get, how much strain you need to make a plastic deformation, how much strain you can apply before it fails, if you have one curve or two curves. So the way that this is set up is you have two strains plotted against each other, and you only need two because by this conservation of volume, you know, and the Poisson ratio it's a fixed value. It no longer it's not as constraining on the system. So this is E2. So that would be E2, strain 1 and 2. The third one is fixed if these two are known. And what you do, this is true. This only works for true stresses and strains, one that keeps into account this change in area, because that's the one that is the fundamental relationship between the stresses and strains. The engineering is convenient, but it doesn't describe the general physics of what's going on. And so what you do is a couple benchmarks exist where you would say, okay, if I was undergoing this uniaxial tension and according to my stress strain curve, it will fail at a given known stress. So you can write this one here. This would be the E1 true that fails. That's a benchmark. That's good to know. Then by this conservation of the volume, you can relate this to the other stress, the other two, because they're fixed, they're coupled. You would say, according to these ratios, that would give you a negative stress right here. So this is where it fails. So that's one benchmark. And then what happens is that you can do these tests like it's an experimental thing. You would have to look at the response of a strain in one dimension and a strain in the other dimension to see what happens. And what gets mapped out is this locus of values where something like this, it forms kind of like this boomerang triangle thing, where anything here, anything above this line is a failure, meaning the material will not survive this amount of stresses due to deformation. So this is the failure regime. You don't want this. I mean, you can't apply this high amount of stress in this direction or this direction. And what's interesting is that you can apply, if you go to this high strain in this region and this amount of strain in this region, it'll survive better than it did if there was only this one direction. So that's one common feature. And then, so anything in here is formable. And then everything here is elastic. So based on this three-dimensional response to stresses, the stresses, you'll get this strain map to guide what your feasible angles are from deformation. Okay, so that's that example. Okay, I'll go ahead and erase this here. Next, we'll talk about forging, where you apply this normal stress of compression into a material to get this plastic deformation into the shape that you want. And it takes high forces, high stresses, because these metals are pretty hard. Okay, so let's talk about upsetting forging. Upsetting means you just have a billet, a cylinder, and you stomp on it in an over some open dies. Upsetting forging. And if you simplify this, so okay, I'll draw the upsetting forging first. You have this billet, a cylinder, starting stock material called a billet. You bust on this billet, so this would be a force of the upsetting applied by the die. And of course there's this reactive force from the die on the other side, equal and opposite of reaction. Then you can quantify this by the height that you start at the beginning of the billet upsetting and the diameter of this billet at the beginning. Then when you stomp on it, of course it's going to, what you're going after is some change in height after the applied force, this force upsetting, and it's going to have a bigger diameter and it's going to barrel out in real life. So this would be the diameter after upsetting. This is the barrel shape. So we can analyze this. There's common models that are applied for this type of analysis, which is simple, but you can use it to get general ideas of this. Even this process we're neglecting a lot. And then you can also extrapolate this simple process to other general forging behavior. So if we were to simplify it by neglecting this barrel, we neglect the barreling, which is in effect neglecting the limitations of lubricants so that the friction, so the friction and basically the friction is the reason why it's barrels, and it barrels because of the lack of uniaxial compression. So we're going to assume we do have uniaxial compression. This upsetting force is evenly distributed across, and the friction is enough to distribute it across, and the friction is enough to prevent the barreling, which is due to this distribution and stresses across the thing. And we're assuming that it's in the plastic deformation. One thing about plastic deformations is that volume is conserved. So the volume here equals the volume there. Okay, when you apply those assumptions, you can describe what is observed. So what if you're to do some testing on your forging process, what you would notice for this upsetting process, if you had a height in meters here, let's say, and you started at this initial height, and then you upset it over several, different tests, and let's say that you ended up at this final height, smaller because you're compressing it, what you would see is that the force, it's not a linear increase in force, it's like an asymptote here. So this would be the force for the upsetting, F'd up force in newtons. So why does that happen? Because of strain hardening. So when we apply this plastic deformation, it's like, you just keep on applying some increasing amount of normal stress, you'll get this elastic behavior. But the goal is to, as soon as you go to some small range, it's going to start to deform in the plastic region. And we know here, it doesn't quantify it, but we know that the material gets harder. And because it gets harder, if we want to increase the height to a significant amount, we have to apply more and more force. So, the model that is applied, it's a fit where so if we were to plot the negative of the stress, the negative of the true compression stress at 1.0, and we would have some quick elastic behavior, and then according to this, it'll start looking like this, similar to this stress strain curve. And for typical materials like this aluminum, something like this, where this would be the true stress. So a model that's typically applied is that for this curve, you can say that the true stress equals some parameters. you would say it's equal to some material parameter and the true strain raised to the n, where K is the material strength parameter. Material strength. And N is the strain hardening exponent. So this is around 1,000. This is less than 1. Typical numbers you'll see for different ductile materials. And so what is this 1? A benchmark for that would be if we're talking about true stress, true strain, it's the natural log of the length change. We can describe it in terms of this height here. It'll be the natural log. Because this is a compression, it's negative, so we can use the absolute value of this ratio. Or the inverse. So the natural, the inverse, yeah, so it's the absolute value of this ratio. The height you have instantaneously upon the known force, the known normal stress, to the original height. If it's a compression, this is going to be a negative, a smaller than 1. Natural log of a smaller than 1 is negative, so you just take the absolute value. And for the 1, that gives you, note, for the original height over the instantaneous height, if that's about 2, if it's 2.7 times less than the original, this true stress, the magnitude of the true stress is 1. So that's what this 1 is here. This means that it shrank by about 2.7 times. Okay. So that's all I had today. Thanks, and we'll see you next time on the Learning Glass Studio.